Okay, we already had a meeting with the non-Turkish speaking students, at least with those who have attended. But at least they should also understand what they are missing. They will be receiving these emails also. Well, we don't have any saying in whether to choose assistance or not. Well, there were basically two factors. One was we had this ÖYP program. And so in my student time, the number of assistants was something like 100. Then we had this ÖYP assistants, and then you said, okay, you are already using the ÖYP assistants, so what I care is the total number. So they reduced the number of the department assistants. And then there were, due to the problems in the last few years, they said they are kind of removed this ÖYP program practically. So they went back. So there was a radical drop in the number. And now they are saying that if you are asking new assistants, you can only ask new assistants for the assistants that have left. But they say that we are not counting the ÖYP assistants. They were not your assistants. Well, you see, the student count now is lower. In the year that I entered the university, and when I was preparing for the university entrance exams, the number of students attending the physics department every year was 180. In my year, it was 140. And it reduced until 70, and then went back up to 90. Well, we don't decide on the number of students. But you see, even if we would be deciding the number of students, I would probably not vote for having less students. I would vote for having more assistants and more instructors. Depends on you. If you have many questions, we can stay until late. If not, I mean, my talk will probably not last more than 30 minutes. My opening. Anyway. Questions? Unfortunately not. You already had your meeting. This will be in Turkish. Yeah, you can practice your Turkish. Yeah, you should complain to your classmates. I'm waiting for them. I mean, if you ask and I answer, it's not a discussion. I will wait for some time and then answer if nobody answers.
No one will answer because it's off.
You never know. Well, there are 100 registered students. What do you think? Ask it in the discussion forum. I mean, you're allowed to discuss the homework questions in the discussion forum. And we might even help.
Yeah. Can I answer?
Not now in the discussion forum. Okay, you see, up to now what we have been doing is we have been trying to build the fundamental building blocks of this new understanding of nature. We had seen that the waves, electromagnetic waves, which we believe strongly that they were waves, we discovered that they are now behaving like particles, and then we also discussed that the particles, like the electrons, we discovered that they behave like waves. And basically the translation between the two descriptions or the two paradigms, you can say that the energy, okay, so let me, the energy of these packet, you see, what we call wave or particle now will be just energy packages. In certain circumstances, they will behave like particles. In certain circumstances, they will behave like waves. And the energy of these packages, or the frequency of these packages, are related to each other. If I can get my tablet working. E is equal to h nu, and the momentum is equal to h over lambda. And you can just read both of these equations whichever way you like. Either the wavelength corresponding to a particle of momentum p is given by this relation, or the momentum corresponding to a wave of wavelength lambda is given by this relation. Similarly, the frequency corresponding to a particle of energy E is given by that first relation over there, or you can say that the energy of the packages or the particles making my wave, whatever wave you are talking about, of frequency nu is given by the first relation. So any questions on those? Now the next task is, well, now we have this new description of nature. Will it be able to explain some of the other observations we have, some of the other puzzles we face with? Now, one of the puzzles was the atomic structure. Now, some of the problems that we were facing in understanding this atomic structure was, well, one of them was an experiment. Was the problem arise when we had this experiment? So you have a very thin foil of gold atoms. And then you have alpha source. Well, alpha is just one kind of radiation we discovered. And essentially the alpha source emits some kind of a particle. The alpha particles.
Is this nucleus of the helium?
Yes, alpha particle is nothing but the nucleus of helium. Some nuclei, they are not stable. They just decay. They just emit 2 protons and 2 neutrons in the form of the stable alpha nuclei. So essentially, compared to electrons, they are very heavy objects, 8,000 times heavier than a single electron. So you just send this alpha particles to a very thin, these very heavy objects, to a very thin foil of gold atoms. And the model we had at that time of the atomic structure was the plum cake model. We had already discovered the electrons, and they behave like point objects, so we have electrons. They are embedded in some positively charged background. This was essentially the picture we had. And what you would expect is, well, this is not very dense. So if you send a very energetic object, it should just go through. Just imagine you have a very thin paper. In fact, what Rutherford had said was it's just like firing a cannon to a piece of paper, and then what you would expect is it should just go through. But what experiment told us is that some of them bounced back. So this was the unexpected results. Well, not many of them bounced back, but some of them did. So that was the puzzle. So how come you send this very heavy, very energetic objects onto a very thin foil of atoms, and some of them come back? And the answer was, the only possible explanation was that this is not the correct model of the atom. The conclusion was that the atom should have a very dense core. So only if it has a very dense core, some of the helium atoms, the alpha particles, if they come close to this very dense core, it should be very small and very heavy, much heavier than the alpha particles themselves, so they just bounce back. So it will be like collision between a very heavy object and a lighter object. So only in that case this can happen. And you can actually calculate, you see, in this model, this is the nuclei with a charge Ze. You just send the alpha particles with a charge 2e. You send them along some line. You don't really know where exactly the alpha part, the nuclei is. You don't know where you are sending the alpha particle exactly. But what happens is here you have many nuclei, and you are sending many alpha particles. Some of them just happen to come very close to the nuclei. Some of them will be far away, so they will just go through. So you just send your alpha particles along this line, and depending on their distance from the nuclei, this is what's called the impact parameter. They just don't go along this straight line since they are pulling each other away. So this is what you will see. This is the alpha particle charge. And this is the gold nucleus. So this is your very heavy nucleus. You send your lighter charged object. As it's approaching the nucleus, it will be repelled. There will be electrostatic repulsion. And it will change its direction. So it will scatter by an angle theta. And then when you put your detector somewhere at a given angle theta, you can determine how many of them move in a given direction. And the number, yes?
Gold, isn't gold all AU?
Okay. It has Z protons. Each proton has a charge E. That's the total charge. And helium is not 2e. B. B is called the impact parameter. And you can actually estimate the number of particles scattering at a given angle, theta. Of course, it will be proportional to the total number of incident particles you send. It will be proportional to the thickness. The thicker it is, the more probable it will come close to some nuclei. It will be proportional to Ze times 2e. This is the force exerted on the helium nuclei, the alpha particle. Well, let me not write all of the constants, but the important thing will be it is also proportional to the fourth power of this sine of this scattering, half of that scattering angle. Now, what does that mean? If you would plot that, it goes to zero very fast. In fact, less than 1% of the particles are scattered by more than 1 degree. That is the theta. So basically, as you expect, as you are sending the particles, most of them, they just go through. But some of them, less than 1%, they scatter by a significant angle, which is kind of the proof that we have a nuclei, a very compact object. You see, in this derivation, what we assume is that the nuclei is just a point object. If it is a point object, assuming that it's a point object, you calculate the number of scattered particles, and this is what you get. And indeed, the experimental data also falls onto this line. So at least within this setup, the nuclei can as well, within this experiment, this result basically shows us that the nuclei can also be just a point object. We don't know the size, but definitely this tells us that within the agreement with this line and the experimental data, tells us that this experiment cannot distinguish a point size, zero size nuclei with a finite size nuclei. Well, let me write the exact expression. So here we have the square of these. N is the density of the alpha particles. No, N is the density of the gold atoms. We have 8 pi epsilon 0 squared. Well, this is basically nothing but the 1 over 4 pi epsilon 0 from the Coulomb force. Then we have R squared. And there we also have the kinetic energy.
R dediğimiz B mi hocam?
No.
Değil.
You see, the number of particles doesn't depend on B. Well, let me also, okay. This is the expression we have. Well, let me draw the experiment again. This is the alpha source. Here you have the foil. And then you have your screen or the detector. This is your detector. It is at an angle theta. So it only measures the particles that are deflected by an angle theta. This is R. So the larger the R, since the particle will be spread, the smaller that the number of particles that will enter through this opening of the detector. So that's why we have that 1 over R squared term over here.
And if it was in a vacuum, would that make a difference? Eğer vakumda olsaydı oraya fark eder miydi?
No.
Değil, değil.
This is probably in vacuum. These alpha particles in atmosphere, they don't propagate much. This should be vacuum.
Yani dağılması probability testi yüzünden mi?
No, you see, consider the light. It comes from a point source. And it goes in every direction. So that is why the intensity will spread on the surface of the sphere.
Yani dalga şeyinden dolayı.
Well, not even a particle. You see, just imagine you have they are not watering the plants today. But let's just imagine they were watering the plants outside. The water just leaves from one point and it goes in every direction. So the intensity of water that falls on the ground at a given distance will also drop by 1 over R squared. It's basically what happens is, let's say you have 4 particles coming for alpha particles. And just for simplicity, let's just assume that they are all moving towards our detector, but at slightly different angles. Their separation between them, due to their different angles, will increase as you go further away, because they are moving like this. So, and their separation, their density drops with 1 over r squared.
Ama tam olarak aynı theta ile dönse,
If it were exactly the same theta, of course, then they would all enter the detector. But you see, you are not sending 4 or 2 or 1 alpha particle, you are sending thousands of them. And they are basically scattering in every angle. They are scattering more with, most of them is not scattering at all, but those who scatter, they basically scatter in every angle. Yes?
As you said, the nucleus is the point particle. Should we understand that as hypotenuse, or we neglect the moving that it's sort of negligibly?
Well, what this, you see, on one hand, you make a computation. It's your model. Your model assumes that the nucleus is a point object. On the other hand, you have your experimental measurements, and you see that they agree. What that tells you is that even if the nucleus has an actual size, it should be so small that it shouldn't be affecting the outcome of this experiment. So it doesn't really tell us that it is actually a point object. What it tells is that with this experiment, with the alpha particles used, we cannot see whether the nucleus has a size or not.
Can we distinguish between two particles? I mean, alpha is approaching the nuclei with this finite b, or it just collides with 0b?
You see, what you do is this one. As I said, you send millions of them. They all will hit the target at different points. What I can actually calculate is this one. So let's say if I have an atom over here, and if I send an alpha particle with an impact parameter b, then I can calculate its scattering angle, theta, as a function b. Now, what I can do is, what should be this impact parameter if my let's just imagine like this. You are sending the alpha particles. Your foil is over here, your detector is over here. Now, what should be the impact parameter so that the sent alpha particle will scatter towards your detector? That is one thing I can calculate. So for a given theta, what should be b? Of course, since my detector is over here, it will have a finite opening. So in fact, if my particle scatters within a range of theta, it will enter my detector, so I will count them. It will contribute to my Ni. But if there's a range of theta, it also tells me there's a range of b. So if you look at it from this side, you see my source target is over here, my detector is over here. I'm just looking at from this side. If I hit such a small area over here, if I target a small area over here, then I can say that my alpha particle comes and scatters into my detector. So then the question is now converted into this one. Let's say, how many of the alpha particles that I send will hit such an area? Because all of those that hit that area will be scattered to my detector. With the same theta. Now, of course, it's not just one nuclei. I have thousands of nuclei. You see, here is my foil. There is some nuclei over here. So if an alpha particle, let's say, hits this point, it will scatter into my detector. If it hits this area over here, it will scatter into my detector. If it hits this area, it will scatter into my detector. Then I can ask this question. What is the fraction of these target areas to the whole area? Let's say if that fraction is 10%, then I can say that assuming the alpha particle beam is more or less homogeneous, 10% of my alpha particles will be scattered towards my detector. That I can say, without knowing the impact parameter of each one of the alpha particles. Yes.
Hani bu bir sıkıntı yaratmaz mı? Mesela kalınlık yer yer değişecek. İlk bölgeye çarpan alfa partiküller daha çok scatter etmesi o bölgedeki homojen de olabilir. Atomic structure random da olabilir ve folyo'nun kalınlığı aynı olmasına rağmen böyle bir şey nasıl yaşıyorsunuz?
Well, you have I'm assuming that at least in 107 you have seen something like experimental error, right? And probably you have also discussed ways of reducing the experimental error. All of the things that you say will contribute to the experimental error. And if you want to avoid them, you would rather try to find a foil which is very close to a crystalline shape so that the spacing will be the same. The thickness, you hope that it will be the same. This experiment didn't tell us that. What this experiment told us was that the atom had a very dense core. That's the only thing it told us. Other experiments told us that in the nuclei, there is the hydrogen nuclei, which we later on called proton. But they are further experiments. But even this one gave us enough headaches. Even this result. You see, now we know that this model of the atom is not correct. This cannot explain that observation from the Rutherford scattering. Then the new model was this one. So we have a very dense core which contains all the positive charge. And around it, we have the electrons. Moving with some speed, let's say v. This was the then new model. Well, what can we say? If the mass of the electron is its speed is v, and v squared over r should be equal to 1 over 4 pi epsilon 0, z times e squared over r squared. We can just cancel the r, so mv squared should be equal to 1 over 4 pi epsilon 0. So this is how its speed and the radius should be related. Do you see any problem with this model? We have an accelerating charge over there. Which means it should emit electromagnetic radiation. So it should lose energy. As it loses energy, it should fall onto the nucleus. But since we all exist, it doesn't. Why not? So classical physics basically couldn't explain it. You see, if you remember Maxwell's equation, your 110 course, you should have seen in 110 course that if you have an accelerating charge, it emits electromagnetic radiation, which contains energy. If it contains energy, then this electron should be losing energy, and in less than 1 second, all the electrons should fall onto the nucleus. But it definitely doesn't do that. So that was one of the puzzles we had. Now let's go back to this experiment. Now we were discussing the size of the nucleus. This experiment told us that at least it could just as well be point-like. And this experiment cannot actually distinguish a point-like nucleus from a non-point-like nucleus. So we can ask the question, how far the alpha particle approaches the nucleus? What is the distance of closest approach? How can we estimate them? Well, we know the kinetic energy of the alpha particle. Let's assume this is given. You have the alpha source here, so you can measure its energy by some other means. But let's say we know that. This is our gold nuclei with Z protons. So what is the distance of closest approach of an alpha nucleus with given kinetic energy to the alpha nuclei?
Equate work done by update and pulsate transmission.
Okay, work done. Well, calculating the work done will be complicated, but what else is the work done related to? The change in the kinetic energy and also the change in potential energy. You see, kinetic energy initial plus the potential energy initial should be equal to the kinetic energy final plus the potential energy final. Well, the alpha particle starts from a very far away distance. So the initial potential energy is 0. So the initial kinetic energy should be equal to the final kinetic energy. What is the potential energy?
Their masses multiplied.
Their masses. Ignore the gravitational force. I mean, the gravitational force they exert on each other will be negligible. Electric potential energy, Ze times 2E over R. Now, what we are looking for is what is the minimum possible value of R. That is the distance of closest approach. But if we are looking for the minimum value of R, that means we are trying to maximize this term. If this term is to be maximum, then this term should be minimum. What is the minimum kinetic energy? 0. So this term should be 0. Yes. It's the kinetic energy, not the energy. So if the kinetic energy is 0, it essentially means that it should stop. So it should be a head-on collision. So this is Ze. The impact parameter should be 0. So we are sending the alpha particle. It reaches this point, and there it stops. So you see these two things are repelling each other. So this is the heavy nuclei. It doesn't move. The alpha particle comes. Since they are pushing each other, it slows down. If it's a head-on collision, here it will stop, and then it will just go back. So it will scatter by 180 degrees. If you are sending a particle, an alpha particle with a non-zero impact parameter, it will come here. Of course, it will push it, so it will change its direction, and it will always have some velocity, so its kinetic energy will always be non-zero, even when it is at its closest distance. So since this will be non-zero, this will not be as large as possible. So if the impact parameter is non-zero, the distance of closest approach will be larger than this R min. Well, if you put in the numbers, this radius R min turns out to be 3.8, no, 3.0 times 10 to the power minus 14 meters.
Can you please say again why the kinetic energy cannot be zero, doesn't become zero when B is not zero?
Yes, let's just imagine this particle. You are pushing it in this direction. It has a horizontal component and a vertical component. So it will gain velocity in the vertical direction. It will keep gaining that. So it will be, its direction will change. So it will definitely have a non-zero vertical velocity all the time. So this will be its trajectory. It's always moving. So its kinetic energy can never be zero. What was the size of an atom? It's 10 to the power minus 10. So what this experiment actually tells us is that if the nucleus has a finite size, then the alpha particles are not reaching that. Because otherwise, we would have seen deviations from the Rutherford scattering formula. It assumes it's a point light. Since we know that these alpha particles are not reaching the nucleus, we actually know that from this experiment that the size of the nucleus, it should be less than this one. If it is as, you see, what is the Rutherford scattering formula? If you look at the derivation, it's in the appendix. It assumes a point-like electric charge. Well, you can assume a point-like electric charge if your charge distribution is spherically symmetric. So basically, this experiment, this Rutherford formula is valid for any spherically symmetric charged object, not necessarily a point-like. But assuming you are outside this sphere, if you go inside, the 1 over r squared law changes. And there's no observation of such change in the first experiment made, at least. So we know that this is the closest the alpha particle approaches the nuclei. And at that distance, it is still outside the nuclei. So that tells us that the nuclei should be smaller than that, at least 4 orders of magnitude smaller than the size of the atom. The actual size turns out to be just 1/3 that one. Yes?
If the electrons make circulation around the nucleus, so there is no spherical symmetry in the charts, so how they still think that there is a circulation around the nucleus?
Well, let's see. Just imagine the electrons as flies. They are so light, they don't influence the motion. They are strongly influenced by the motion of the alpha particle, but they don't influence the motion of the alpha particle. They are so light. They are 8,000 times lighter in mass than the alpha particle. So the only influence on the trajectory of the alpha particle will be the nucleus. So in that derivation, we basically ignore it. It's a part of the experimental error. Which you should estimate.
So the circulation of electrons doesn't oppose the assumption.
No. You see, here the main influence on determining the trajectory is the nucleus itself, not the orbits, not the electrons. So it's important that the nucleus should be more or less spherical. It doesn't have to be exactly spherical, but if there's any deviation from sphericity, this measurement doesn't see it. Any other questions? Now you see, we made one experiment. It's this Rutherford scattering experiment. And then we have an explanation for that experiment. This Rutherford scattering formula quite successfully explained this scattering observations. No problem with there. But then this explanation itself arises this problem. There are charges, accelerating charges, which are not emitting electromagnetic radiation. So that's one problem that we have to address. Another problem related with this electromagnetic radiation is here we have the non-emission of electromagnetic radiation, but there's also the problem of the emission of electromagnetic radiation. You see, we had already seen the blackbody radiation. And one thing we had seen in the blackbody radiation is that it doesn't matter what kind of material you use. The only thing is that if it is a good enough approximation of a blackbody, it emits all frequencies with given intensities, etc. It doesn't depend on the properties of your system. But what that tells us is also that it's mainly a collective phenomenon of the system as a whole, not just not the specific atoms making my system. It's independent of the properties of the atoms. But we can go to the other extreme. We can just consider a very rarefied gas of some elements. I don't know how it's written. That's probably the wrong spelling. So you just have a very low density gas, like the neon lamps. That's essentially what the neon lamps are. So you get a very low density gas. You send some electric current through it, and then you get some light. You send some electric discharge, through this gas, and then you get the light, send it through a prism. But this time, what you will, if you just do send sunlight through the prism, you get all the frequencies, all the lights, all the different colors. But if you send this light through the prism, you just get discrete frequencies. This is called the emission spectrum. Or you can do something else. Take the same gas, send some sunlight, and take the light from the other side, and again send it to prism. You get another spectrum. Exactly at the same points, you end up having gaps. Again, you get almost a continuous spectrum of colors, but then there are gaps. And these gaps coincide exactly with the lines that you obtain in the emission spectrum. This is called the absorption spectrum. And in fact, even if you take the sunlight, where? We will discuss. Ask it later on. Depends on the frequency what you will observe. If you take the sunlight, okay, you get all the colors. But if you look at these more carefully, you still see some gaps. So why are those gaps? Why are those gaps at the particular places they are? Sure. You see, this phenomena of the absorption spectrum over here and these gaps, they basically originate from the same thing, as your friend pointed out. You see, when this, if you consider the sun also has an atmosphere. Which is dominantly hydrogen, but there are also other elements. So when the light leaves the sun, it passes through all this atmosphere. So here we are putting some additional gas, not necessarily hydrogen in this case, but which creates these gaps. In the case of the sun, without any additional rarefied gas, well, the gas is already there. So in fact, this is one of the ways we know that at least the other stars, we can determine their composition by looking at the position of the gaps. And looking at the gaps, we can identify which elements are there. And once we determine, and they are also abundances, and then we can say that a given star is made up of mainly this and this material. And it also tells us that most probably the laws of nature are the same everywhere, because we basically observe the same spectrum, more or less the same spectrum from most of the stars. And then we can even identify, you see, the hydrogen, for example, just emits, when you look at its emission spectrum through this, it emits at particular frequencies. Well, if the star is moving away from us or towards us, there will be Doppler shifts. But that Doppler shift will shift all the lines. So still, even if they are shifted, we can identify which line corresponds to hydrogen and which line corresponds to other elements. And by looking at how much they shift, these lines shift, we can determine their velocities. And in fact, when they were studying the spectrum of sun, they discovered several, let's say, if this is the spectrum, there was some missing line over here, another line over here, some other line here, some other line here, etc. So these are all the missing lines. And what people discovered was all these lines can be expressed by a very simple formula. Now, let me write properly. Yes, 1 over lambda is just 1 over r, no, just r, so-called the Rydberg constant, 1 over 2 squared minus 1 over n squared. This was a very simple expression. These are the lines in the visible range. At the time, we didn't know. These are called the Balmer series. Okay, let me not confuse the names. No, these are the Balmer series. And this R, it was experimentally measured to be 1.097 meter inverse. Well, you see, as a nice, curious person, your friend asked, what does 1 stand for? Well, it turns out that, what does 2 stand for? It turns out that 2 is not so special. There were other such lines which were given by the expression 1 over 1 squared minus 1 over n squared. These were the Lyman series. But you see, these are not in the visible spectrum. So the first people didn't see these. Being in the visible spectrum, this was the easiest one to discover. Then your friend you should probably ask, what is special about 1 and 2? Why not 3? Hmm? So you see, for the time being, these are just observations. Observations that need explanations. Hmm? Why squares? You see, these are the questions we had. Why are they just squares? Why not cubes? or the fourth powers. They didn't exist, only the differences of the inverse squares of integers. Why differences of squares? Why integers? Why not some number containing pi or e? Yeah, we will eventually be led to the energy levels. When we discuss the Bohr's model, we will be able to explain all these. But as I said, we have some new understanding of nature now. At the beginning of the 1900s, let's say, we have this new understanding, and there are new puzzles that we should try to understand. So what you do is you just apply what you have learned into these. You see, that is one of the fascinations I have. You see, at the end of the day, you just have the wavelength corresponding to these lines. How can somehow you come up with the idea of expressing them in that form? I have no idea. Another one of my fascinations is Kepler's laws. Okay, once you have the Newton's laws, they are always almost straightforward. But Kepler discovered his laws beforehand, at a time that people thought that the Earth was the center. You see, if you are being subject to astrology news, almost all the newspapers in their front page has these astrology news, you probably heard of the terms of the Mars retro, for example. You have heard of it? So, because if you look at from Earth, what Mars seems to do is it moves in one direction, and then after some time it starts moving in the opposite directions, and then continues in its trajectory. That is how Mars looks. So that's the retro. But now we know that if you put your center on the sun, it's just an ellipse. So, but how would you think of putting the center to sun? Just looking at this data of retros, etc. So how did they come up with these formulas? I have absolutely no idea. But at least that is what they have. And it's also interesting, why do they all have the same constant? Is it a new fundamental constant of nature, or can we express it in terms of the other constants that we already know? You see, up to now we know the Boltzmann constant, we know the speed of light, we know the charge of the electron, and we know the Planck's constant. And now there is this Rydberg's constant. Is it a fundamental just like the other ones, or can we express this in terms of the other ones?
Bunlar gerçek sabit olsaydı girimsiz olmaları gerekmiyor mu?
Why?
Yani mesela zayıf nükleer kuvvet ya da işte değişim kuvvet, onlarda birim olmadığını hatırlıyor musun hocam?
Well, let's see. The Newton's constant has the units of the newtons meter squared per kilogram squared.
Bunlar conversion yapılması için kullanılan constantlar. Yani doğanın kendi constant olduğunu düşünmüyorum.
Okay, fine.
Yani şey anlamında da bunlar dönüşüm için kullanılan constantlar. Mesela G, R. Yani bir birimden Newton'a geçmek için sağlıyor.
You see, the problem is this one. What your friend is pointing out is the Rydberg constant is 1 over meter. How long is a meter? How long is a meter? Show me. Yeah, this much. 1 meter is just the size of an arm. Well, why should the atom care about the size of the human arm? So we have such stupid stupid units to describe nature, so that we end up having such 1.097 times 10 to the power minus 7. No, 10 to the power 7 meter inverse. A more natural unit, I would say, what about the Compton wavelength? You can say, you can express R in terms of some multiple of Compton wavelength, for example. That would probably be a more natural unit. Or the size of the atom. That would probably be a more natural length unit. Okay, any questions? A 5-minute break. We will start at 40. We will have fun in the next hour.